So today is the fourth out of the seven lectures in the series for Energy Conversion Systems M. And today everything is going to be about solar generation. So that's both about thermal solar, and that's probably the one that is less talked about solar, but in fact, it's probably the one that's got a bigger impact on solutions to climate change than in fact photovoltaics. Photovoltaics is taking solar and the direct turning of solar energy into electricity. So we'll talk about both today, and you'll see by the end why thermal solar is probably a more important technology to think about. So the things that we're going to learn today, the amount of energy that's available from the sun, and not just directly from the sun, but at different points on the planet. And it varies a little bit, and we'll discuss that and give you the ability to work out how much energy is available wherever you are on the planet. The use of solar energy for thermal heating applications. So that's something that's maybe not so useful in every country, but it has an enormous impact, certainly in Western countries and certainly in the UK. How photovoltaic solar cells generate electricity, and what is the optimum absorption wavelength, as well as how can we maximize the electrical generation efficiency. So there's quite a lot of different topics to go through today, but as you'll see, it's really getting down to two key areas of solar generation that we're going to talk about. So overall with solar energy, there's four major types of applications. Now, in the previous lectures, we've spoken a bit about solar biomass and using trees and plants to make fuel through photosynthesis and how to have those being sustainable. There's also, of course, food and the use of solar in the generation of the chemical energy through photosynthesis, particularly in plants. Now, we're not going to talk about solar biomass or food anymore in this course. We've already covered them sufficiently for the course. Today, it's very much about solar thermal with the direct heating of buildings or the direct heating of water to be used in buildings. And then the second half is going to focus solely on solar photovoltaics and the direct generation of electricity using semiconductor materials. So how much energy is available? Well, to be able to work that out, we need to look at the physics of what's known as black bodies. Now, a black body is really a theoretical construct to be able to understand how much energy is emitted and absorbed at different wavelengths of light. So it's not a real system. You're really idealizing the system and making it perfect and making a system with zero losses. Of course, in reality, there's always going to be some losses in every system. So a black body emits photons of light with a distribution of energy, and energy is just Planck's constant. That's H, which is 6.67 times 10 to the minus 34 joule seconds, times the frequency of the photons. And the frequency for most of the photons we're talking about today is going to be petahertz. So that's 10 to the 15 hertz. And that is determined by the object's characteristic temperature T. So what the black body emission properties that Planck derived at the end of the 19th century and the start of the 20th century, if a body has a temperature, it's going to emit photons of energy. Some of those photons will be infrared and what we know as heat, and some of those photons could be mid-infrared, near-infrared, or in the visible part of the spectrum, ultraviolet, or X-rays at higher energy. So Einstein showed that the energy of a photon is Planck's constant times the frequency. We've got the wave equation. So the wavelength of the photons equals the speed of light. For all photons, that's going to be 3 times 10 to the 8 meters per second in terms of speed, and divided by the frequency in hertz. So what Planck derived is this equilibrium photon energy density. So this rho is for energy density. It's given at a particular energy, where we've written the energy here as Planck's constant times the frequency. And you can see we get a formula that gives us a distribution of the energy in terms of the frequency, and it goes as the cube of the frequency divided by an exponential with the frequency divided by a thermal energy term. So I'll show in the next slide exactly what this looks like. But here we can just choose a temperature for any black body. And if we put it into this equation, that gives us an easy way to be able to work out exactly how much energy density is available as a function of the energy of the photons. Now we can write this in a couple of different ways, some of which are more useful. This is typically the formula that's used when you need to integrate up to understand how much energy is being emitted, let's say from the sun. Or in fact, you could do this for a person, you could do it for any body. So we actually emit heat, and that heat can be determined just using these equations and putting in room temperature or the temperature of our body at 37 degrees C into these equations. So everything emits black body radiation. Light bulbs emit it, the sun emits it. It just depends on the temperature of that body at which frequencies and where the energy is available from different black bodies. So it's probably easier when you actually see what these spectra look like. And this is the spectrum from the sun. Now the sun can basically be modeled by a black body at 6,000 Kelvin. So when you use the black body equations, you always have to use the absolute temperature, and it always has to be in Kelvin. We'll talk about these air mass zero and exactly what that stands for, but air mass zero is actually what you get at the equator before the sun's light enters the atmosphere. Now, that green curve is actually the black body equation from the previous slide with 6,000 Kelvin put into it as the temperature. And you can see this is the sort of curve that we get out. The red is actually the AM0 measured in a spacecraft above the equator and the sun's solar spectrum outside the Earth's atmosphere. And you can see that it matches pretty well, not exactly, but it matches extremely well. And in fact, for most applications, the theoretical curve here is certainly good enough to model solar systems. The blue one is what we actually have at 37 degrees C latitude, and I'll explain how these numbers come out a little bit later in the lecture. But what you can see when you're on the Earth's surface is now we start to get absorption of the light at very specific frequencies. And in fact, these frequencies that you're seeing here are related to water molecules absorbing the light. So this all relates to H2O and the vibrational modes of the light being absorbed by water. So the first thing I want to do is talk about what is the maximum efficiency of any solar use of energy. So we're going to look at the Carnot limit for radiative absorption. What we really want to think about is the sun, which is a black body emitting with an equivalent temperature of 6,000 Kelvin. Now, the black body equivalent temperature is not the same as the temperature of the sun's surface itself. So the 6,000 Kelvin is just the temperature that gives the correct solar spectrum coming out in terms of the frequency and energy distribution. We then want to consider a black body on the Earth that will absorb all the photons. Now, when we talk about a black body absorber, what we're really talking about is something that can absorb all the photons. Now, in any practical system, there's going to be some reflection. It might only be an extremely small percentage of the photons in the system, but there's always going to be some loss in any real system. The other thing with the black body system we need to consider is the photons go into what's normally considered to be a black body cavity. So everything absorbed, and then every photon gets turned into heat. And there is no thermal dissipation or thermal loss from this black body. So to calculate the Carnot limit for solar systems, what we're really doing is considering every photon being absorbed, being turned into heat energy, and none of that heat energy being lost to understand what the maximum possible efficiency of an idealized system could be. Now, in fact, a black body absorber, it's not at 27 degrees C around room temperature. What we need to be thinking about is, in fact, we need to increase the black body temperature, in fact, to 2,470 Kelvin to get the best impedance matching between the sun and the black body absorber. Now, this is one of the reasons why the actual Carnot efficiency, if we look at a black body absorber at 300 Kelvin, is going to be less than 85%, but the maximum possible efficiency of taking solar energy and converting it into any other form of energy is 85%. So the actual efficiencies we're going to see are going to be less than 85%. So this is a number to remember throughout this lecture. When we talk about how efficient the different systems are, you can see how many are quite close to 85% efficiency and how many are very far away from that and perhaps have opportunity to be improved. Well, let's just look at the solar spectrum in a slightly different way. And this time we're going to think about it in energy. And I've just changed this around from the wavelength I showed earlier. And what I've got now is the photon energy down the bottom. What I've also put in is where the red, green, and blue parts of the visible are in the spectrum. So these are the visible parts of the spectrum that we can see through. And it's also why we can see the sun. And of course, the effect of white light that comes from the sun is made up of all the different colors mixed together. And in addition to the visible part, there's also the ultraviolet, where there's photons at higher energy than our eyes can see. And also a lot of photons in the infrared, heat photons, if you like, because they transfer energy that is not visible to the human eye, but they can heat bodies quite significantly. So if we only pick up light from the visible, from the sun, you can see we throw away a lot of energy that our human eye cannot visibly see. Now, the amount of solar energy that is available is not the same at every single point on the planet. Now, this is not just because of cloud cover. So we always joke in Glasgow that it's never that sunny in Glasgow compared to many other parts of the world. So, solar energy maybe doesn't seem that good. I'll give you the numbers later so you can understand at different parts of the world just how good or bad the amount of solar energy is. But the biggest thing that matters is that the sun will sit above the equator, and depending on the different latitude you are on the globe, the photons have to go through the Earth's atmosphere, and the higher in latitude you are, or the lower in latitude if you're going to the South Pole, the photons have to go through a larger part of the Earth's atmosphere. Now, in the Earth's atmosphere, there can be scattering. There can also be absorption from the gas molecules, the water molecules, dust particles, and so on. So that the further that the photons have to travel through the Earth's atmosphere, the less photons become available on the Earth's surface. So that's really the major part of why there's less light as you go further away from the equator. Now, the way we work this out is we just create an equilateral triangle. We set the sun to be above the equator, and we define what's known as the air mass index. So this N in the air mass index is the optical path length to the sun divided by the optical path length if the sun was directly overhead. So the denominator in here is the distance of the atmosphere times the air mass index. So what we've done here is we define what's known as the zenith. So this is a term from astronomy, and the zenith is an imaginary point directly above a particular location on the Earth. So we have gamma, which is the angle between the zenith to the angle looking directly at the sun. Since this is an equilateral, or these are both equilateral triangles, this also equals gamma in here. So this is 90 degrees minus gamma, hence being an equilateral triangle, and that's 90 degrees. This has got to be gamma in here. So if this is d atmosphere, and that's d atmosphere times the air mass index, cos of gamma is just the nearest times the hypotenuse. So it's the depth of the atmosphere divided by the depth of the atmosphere times the air mass index. Now, if we turn this around, these of course just cancel, and the air mass index is just 1 over cos gamma as defined here. Now, there's a convention that, partly for historical reasons and partly because the National Institutes of Standards and Technologies in the US has its major solar center at 37 degrees latitude in Boulder, Colorado. But to allow comparison between all solar cell technologies, all solar cells are compared to AM 1.5. Now that latitude is basically also appropriate for Spain, for parts of France, for parts of Italy. You can go around the planet and there's many different places in a lot of different countries that are AM 1.5. So this is by convention, and it really just provides a standard that every single solar cell that is produced can be tested with the same conditions, so there can be a direct comparison over how good or how bad all the different cells are. Well, more realistic spectra. So we spoke about air mass 1, and that's the spectrum at the equator on the Earth's surface with the sun directly overhead. Now, of course, the Earth's axis is rotated slightly from being completely perpendicular to the sun. And this is why you end up actually having the maximum sun at the spring and the autumn equinoxes and not in the middle of the summer. If we look at AM 1.5, that's receiving where the surface is inclined at 37 degrees from the horizontal towards the equator facing south. So if this is our zenith, that's our sun up the top. In fact, the normal from the Earth is not the zenith. And that's probably one of the things that confuses students the most if they haven't done astronomy and they have never heard the term zenith previously. So if this is our 37 degrees for the latitude, our point on the Earth, we can go through with this and our right angle triangle to define the zenith. From there, we can work out where the sun is going to appear. And for 37 degrees, it turns out to be 41.81 from this horizon. Or if we do it from the zenith, it's 48.19 degrees from the zenith. So this gives us, for the air mass index, 1 over the cos of 48.19 degrees. And that's where the 1.5 for the air mass 1.5 comes from. So when you look at other latitudes, I would suggest you take this diagram. And for instance, Glasgow is roughly 60 degrees. You put 60 degrees in here, and then you change all the numbers for that. You can work out what the air mass index, and you can do it for any other latitude on the planet. So as I've said, 37 degrees is the average latitude for Boulder, Colorado in the US. The zenith angle for that is 48.19 degrees, and the elevation angle from the sun is 41.81 degrees above the horizon. So this is worthwhile just going through after the lecture and just going through and understanding the right angle triangles and how all the numbers work out in the geometry of the system. So far when we talk about solar cells and we think about solar energy, we're probably only thinking about the direct sunlight and the photons that come through the atmosphere and directly hit our photovoltaic or the solar thermal system. And in fact, the majority of energy that gets collected in any of these systems, particularly for solar cells or thermal systems outside, comes from the direct sunlight, 83%. But there's also the different particles in the atmosphere. 20 to 40 kilometers above the Earth's surface is where the ozone layer is. There's air molecules, typically between 0 to 30 kilometers. So that's predominantly nitrogen and oxygen. There's also a lot of dust. So whether it's sand or other dust particles, that's typically between 0 to 25 kilometers. And water vapor, actually the majority of water vapor is only within 3 kilometers of the Earth's surface. So in fact, there's a lot of different molecules and particles that make up the Earth's atmosphere. And many of those particles can absorb and re-emit photons, or can scatter, diffusively scatter light, so that even non-direct light can actually be scattered onto your solar collector and be used. Now, buildings, mountains, trees, vegetation, there's a lot of different systems as well that can scatter light. So typically about 17% of the light is diffuse and non-direct, but that will vary depending where you are. In cities, it's a very different number from being out in a desert or being on top of a mountain. So it will vary depending where you are on the planet. What's known as the global irradiance, and that's the number you're interested in for the useful energy you can collect and potentially use, is the direct plus the diffuse added together. So this is really just defining the problem, and you will see that, for instance, if you want to use a photovoltaic to power a calculator or power a watch indoors, it's only diffuse light that you're going to collect. You may get some direct light from light bulbs, but the majority of light you're using is probably diffuse light. So how much energy and what wavelengths? Well, I've shown this spectrum before, but I haven't actually told you how much energy is available if you integrate this all up. So if we are at AM0, which is this red curve here, and we're above the Earth's atmosphere at the equator, you have 1,353 watts per meter squared surface area over all the wavelengths when you integrate up this red curve. So that's the maximum possible solar energy you could have if you're just above the Earth's atmosphere. Now, of course, as I've said, the Earth's atmosphere is going to absorb, and you can see with these real spectra here, you've got the global and the direct coming in. So the global includes the diffuse. And in fact, the other reason that AM 1.5 is used as the standard is that AM 1.5 is almost exactly 1,000 watts per meter squared over all wavelengths. So this is not just because of the US NIST laboratory being at that latitude. It actually turns out this is a nice, easy way to remember the standard test for any photovoltaic cell, that the amount of energy is 1,000 watts per meter squared. Now we'll talk later in the lecture about the conversion efficiency, but that, at least at 37 degrees latitude, when you get to noon in a day, that's the maximum possible available. So that gives you an idea that we're talking about a kilowatt per meter squared of energy available that you could potentially use for applications. But this is not the same all over the Earth. So here are some examples. Now we joke in Glasgow that photovoltaics you only really use to keep the rain off the roofs, but actually it's not quite true. even in Glasgow, if we, instead of having the peak value, what this slide is showing is the continuous solar energy that you have when averaged over 365 days and 24 hours. So in Glasgow, the average you get is 94 watts per meter squared if you consider integrating up over 365 days. If we do that for London, it's about 108. Paris is 128. And we can go down. You can hopefully, depending which countries you are in the world, you can go through and look at the different latitudes, and you're probably quite similar to a number of these places. But the highest recorded average solar energy that's available on the planet is at Nouakchott, which is the capital of Mauritania in the Sahara Desert. And that has a value that's about 270 watts per meter squared when you average over 365 days and 24 hours. So the peak that you're going to get, certainly at Nouakchott, is over 1,000 watts per meter squared, but that's the peak that you'll get. And when we average over nighttime as well, and some days when in the Sahara Desert, there will be days with clouds, very few compared to Glasgow, but you will still have some days where the solar energy is much lower than the peak. So this gives you a better idea of the continuous availability of solar energy over the whole year. So it's not that each day in winter, you're going to have the same amount as each day in summer. There's more solar energy available in summer because the days are longer than the days in winter. That's going to vary depending where you are on the planet, but you cannot guarantee solar 24 hours a day. And this is one of the problems of solar energy. Now, that's the numbers at different parts on the Earth's surface. This is an example. It was a European project that actually just looked at 8 particular very sunny parts of the world. And at these 8 different parts, there's actually sufficient solar energy to power the whole of the Earth's consumption of energy, at least between 1991 and 1993. Now, the total consumption on the Earth of energy has gone up. It's not gone up that much, but you only need 8% conversion efficiency to take the solar energy at these 8 spots and use it for the whole planet. So why don't we do that? Well, you'll see in the last lecture, cost is one of the issues with solar. The other thing is that the consumption of energy around the planet, a lot of it is not near these 8 spots. And as we showed in the second lecture, electricity doesn't travel very well. So if we capture solar energy, let's say down here, if we want to use it in the UK, that's not very practical at all. And this is one of the real problems with solar, that where a lot of the consumption of energy is, it tends to be where solar energy is lower compared to many of the hotter climates in the world, where consumption is a lot less. So we'll discuss a bit more about that in the next section of the lecture, but this is a good point to have a break. I will stop the recording